Let us now consider another example of electric stress control in a very common configuration that we often see in the laboratory as well as in power systems apparatus, where we have coaxial cylinders. Coaxial cylinders are electrode configurations which are very common in high voltage. For example, you have high voltage cables. In high voltage cables, you have a conductor at the core. Over and above that, you have a concentric cylinder of insulation, and then the outer casing, the outer sheath of the cable is there. So these are all which is grounded. So then you have concentric cylinders, and you have a potential difference across these concentric cylinders. Another instance of where you would very often see concentric cylinders or coaxial cylinders is in the case of a gas insulated line. Now, we have generally been talking about air insulated transmission systems or air insulated transmission lines, where the transmission lines are out in the open and the air that is around it provides the insulation. So all we have to do to design the insulation is provide enough clearance. But this takes air obviously has its advantages, but you may need quite a bit of clearance to provide adequate insulation in case the voltage is very high, in case the transmission voltage is very high. And therefore, we are now looking at gas insulated transmission lines. We will talk about gas insulated transmission lines later in this course. Right now, let us just consider what these gas insulated transmission lines or gas insulated substations are. Here we are going to use pressurized gas instead of air as insulator. This pressurized gas could be nitrogen, could be SF6, could be mixtures of nitrogen and other inert gases, etc. And very often they are not at atmospheric pressure, they're at higher pressure. Now, why do we use these gases? We use these gases because they have a higher dielectric breakdown strength, and as a result, we would need lesser quantity of insulation for the same voltage level. Of course, there are other advantages also, which we will not discuss now. So the point is that if you're going to use pressurized gas instead of air, you need an enclosure. So in gas insulated lines, you have a conductor running through, and to insulate that conductor, you need gas. So you need a metal enclosure, which is most often cylindrical, and that is earthed. And in the space between the conductor and the enclosure, you have the insulating gas. So we have a lot of situations where there are coaxial cylinders. Now, what kind of distribution would you expect around or inside a coaxial cylinder? Let us consider this case. We have an inner cylinder of radius R1 and an outer cylinder of radius R2. These are coaxial cylinders. You can imagine this to be a cable with the insulation inside here between R1 and R2. So analytically, the electric field in the space between R1 and R2 can be calculated as EX equal to Q by L, Q being the charge per unit length, Q by L being the charge per unit length, divided by 2 pi epsilon into 1 by X, which is written as V, if V is the potential difference across the conductor, which is caused by the charge Q, V by Ln R2 by R1 into 1 by X, which means the electric field reduces with distance from the conductor, from the radial distance from the center. If that is the case, then the maximum fields will be obtained at the surface of the inner conductor. So Emax is equal to V divided by R1 ln R2 by R1. This is an expression in terms of the radii of the concentric cylinders and for the maximum electric field, which is observed at the surface of the inner conductor. Next, as a contrast to coaxial cylinders, let us consider a similarly popular arrangement, and that is a spherical cylinder. A spherical concentric spheres. So spherical arrangements with the concentric spheres. So here you have similarly an inner sphere with radius capital R1 and an outer sphere with radius capital R2. So similarly, as before, we will be able to obtain an analytical expression for the electric field in the space between capital R1 and capital R2. This is given by Q by 4 pi epsilon 1 by x square. So the electric field reduces with radial distance from the center, but this is inversely proportional to the square of the distance. So this electric field reduces much faster. So that is a good thing in contrast to a cylinder. In a cylinder, as you're going away, the electric field from whatever maximum value you have, it is reducing linearly, and in this case, for a sphere, it is reducing faster. It is reducing at the rate of square of the distance. Again, so this can also be written as in terms of the voltage. This Q can be expressed as EX is equal to V by R2 minus R1, that's the gap distance, divided by R1, R2 into 1 by x square. Again, this value will be maximum at the surface of the inner sphere. So when x is equal to capital R1, which gives me an expression for the maximum value of the electric stress for a spherical configuration, V divided by R1 into 1 minus R1 by R2. Normally, R2 will be much larger than R1. Let us imagine that R2 is much larger than R1. We will discuss some situations where this is a very reasonable assumption. If that is the case, then we can approximate Emax as V by R1. Now, if you compare the maximum in the two configurations, in both cases, the maximum electric stress occurs at the surface of the inner conductor. However, the Emax has a higher value for the spherical configuration, and it will be, if you have the same geometry, same radii. So let us imagine that small r1 is equal to capital R1 and small r2 is equal to capital R2. So we are using the same radii for the inner cylinder and sphere and the outer cylinder and sphere. In that case, if you compare the maximum fields in the two situations, the maximum fields will be higher for the spherical configuration. So when you are designing the insulation, if you have two geometries of similar, two configurations of similar geometries, you have to be more careful about the spherical arrangement. You have to make sure that the spherical arrangement is so designed, that breakdown does not happen on the surface of the conductor. Now, as I said, let us imagine that the insulating medium is air. In that case, the maximum electric field is obtained at the surface of the inner conductor, and this can be obtained as V by R1 approximately, since we have assumed R2 to be much larger than R1. How do I decide what is an acceptable stress at the surface of the inner conductor? It should be lower than the breakdown value of air, because otherwise breakdown will happen, and once breakdown happens, at one point things can go awry. So what we would like is that the maximum electric stress that we obtain at the surface of the inner sphere should be lower than the breakdown strength of air, if we are talking about air. Now, air has a breakdown strength of 30 kV per centimeter. However, in practice, you will not really be able to achieve this kind of a high breakdown strength. And that is because in practice, you will not be able to control all conditions. You will not be able to control ambient conditions. So there will be moisture in the air. There will be dust particles present. There might be pollutants in the air. There might be contamination on the insulator surface. There might be dust particles on the insulator surface. So there might be many spurious reasons, and therefore it is safe to assume that instead of 30 kV per centimeter, assume a breakdown strength of 12 to 15 kV per centimeter for air. So if you design your insulator considering the breakdown strength of air to be around 12 to 15 kV per centimeter, then the chances are that breakdown will surely be averted. And therefore, we would like Emax to be half the breakdown strength of air. So this is a good guiding principle for what kind of dimensions you would like to use for your spherical configuration, so that the maximum electric field at the surface of this inner sphere does not cause breakdown if you have air as an insulating medium. If you can ensure that, and then with the same configuration, that small r1 equal to capital R1, if you design a cylindrical configuration, you are safe, because the Emax at the cylindrical surface will always be less than the Emax at the spherical surface. So if the sphere is designed to withstand breakdown, then a cylindrical configuration with the same radius will definitely be able to withstand breakdown. So this is a discussion about coaxial cylinders versus spherical configurations. Let us see how this becomes useful in practice. Now, when we have coaxial cylinders, we often have coaxial cylinders to provide supply, to take supply from one point to another. Even in the laboratory, let's say I'm going to perform a dielectric breakdown test, and I want to take supply from my high voltage transformer to the test object. In that case, I might use a cylindrical conductor. That is because it is easy to design PD-free connections in high voltage circuits. Why PD-free is important, we will discuss later. But when I take the cylindrical conductor and extend the supply from one point to another, at some point I need to truncate the cylindrical arrangement. And when I need to truncate the cylindrical connection, cylindrical conductor, there will be a ragged edge. There will be a sharp edge where I truncate the cylinder, and there will be likelihood of discharges in this region because of local field intensification. So I will never do this. I will never truncate the cylinder and leave it like that. Instead, what I will use is I will use an end termination. I will use an end conductor. And normally this is a sphere of larger diameter which is located at the ends of the cylindrical conductor. Why larger? Because you remember, if you design the cylindrical conductor such that there is no discharge on the surface, and you put a spherical conductor at the end with the same radii, the maximum electric field on the spherical conductor will be higher than that on the cylindrical conductor, and this can lead to breakdown. So normally end terminations are obtained by putting a sphere of larger diameter than that of the cylindrical conductor and capping that. Now let us see whether we can get some estimate about what the field would be like if I have this kind of a configuration where I have a cylindrical conductor, a long cylindrical conductor, which is ended by a spherical conductor of a larger dimension. Now, in this case, you do not have a coaxial situation. You do not have coaxial conductors. You do not have concentric conductors. You have a single cylinder which is ended by a single sphere. But we can still use, kind of as a first approximation, we can still use the discussion we have had in the previous slide. That is, we can consider this to be an arrangement of coaxial cylinders, where one of the cylinders is your cylindrical conductor, that is the inner cylinder, and the outer cylinder is formed by the earth walls of the laboratory. Compared to the radius of the cylinder, the radius of the earth walls of the laboratory would be very large, especially in a high voltage laboratory. High voltage laboratories are generally have very high ceilings. So the walls will be very far away, and the fact that it's not generally a cylindrical laboratory will cease to matter. So you can approximate the walls, the room walls, as an outer cylinder of the cylindrical conductor. Similarly, for the spherical end conductor, you can imagine the room to be spherical in shape. The outer walls forms the outer sphere. Your spherical conductor forms the inner sphere. So what we will do is we will use the discussion we have had regarding maximum electric fields for spherical and coaxial cylinders, and we will try to estimate the fields at the surfaces. So the earth walls of the laboratory will form the outer diameters of the sphere and the cylinder, and we may approximately assume that the field distributions at both the electrodes are independent of each other. That means the cylindrical region is not affected by the presence of the spherical conductor, and vice versa. So we are going to make this assumption. Now what we would like to do is we would like to equate the maximum value of the electric field. The maximum value of the electric field will occur at the surface of the cylinder and the sphere, and we would like to equate these two values so that we are kind of optimizing the arrangement to the best of our ability. Why is that an optical arrangement? I'll come to later. So we would like equal maximum values at both the surfaces. So therefore, Emax for cylinder is equated with Emax for the sphere, which gives me V by R1 ln R2 by R1. These are of course both at the same voltage because it's the same conductor. Capital V by R1 ln R2 by R1 is equal to capital V by capital R1 1 minus capital R1 by capital R2. This gives me this expression. I can write this as get rid of V from both sides, cancelling out both sides. So capital R1 by small r1 is ln R2 by R1 divided by 1 minus R1 by R2. Now, when you are considering the walls of the laboratory, there is no question about the fact that R2 is much larger than R1, and therefore this ratio R1 by R2 will be much smaller than unity. So you can neglect that. So therefore, capital R1 by small r1 would be approximately equal to the logarithm of small r2 by r1, which means what we are setting up is we are setting up a dimension, a required dimension for the radius or the diameter of the spherical end termination. So you have a cylindrical conductor with a radius small r1. You are trying to figure out what should be the radius for the end termination sphere. And using this configuration, where I consider the outer walls as the outer cylinder and the outer sphere, I obtain this expression that capital R1, which is the radius of the spherical end termination, should be equal to R1 into ln R2 by R1. So I am able to obtain the dimensions of R1 in terms of the radii of the cylindrical portion. Of course, it does not only have R1 in the expression, it also has small r2, and small r2 or capital R2 are the same. They are the walls of the laboratory, so they are the distance from the center of the conductor to the walls of the laboratory. And it is safe to assume that the radius R2 or capital R2 of the laboratory will be about 20 times the radii of the electrodes as a rough estimate. If you consider, it may be larger, if you consider that small r2 is 20 times small r1, which means capital R2 is also 20 times small r1, then this ratio ln R2 by R1 should become at least 3. If you satisfy this arrangement, that is capital R1 is 3 times the small r1, then you are safe. You are not going to have discharge at the surface of the spherical end termination. You are well protected. You have effectively controlled the stress intensification that is likely to happen. Remember, this is only true for large electrodes. If you have very small electrodes with very small diameters, then this kind of analysis is not going to be useful. We would actually have to compute the electric fields, taking into consideration all the details, and find out what kind of fields we expect. So in that case, this thumb rule is not going to work. You have to do a proper numerical computation, because of course most of the time analytical computation will not be viable. So this is how we can figure out what kind of end termination we need to decide for a cylindrical conductor. Now, to extend this discussion, let us consider the case of busbars. Bus bars are especially important with respect to the gas insulated substations that I was talking about. Now, in gas insulated substations, you have all the equipment, all the apparatus enclosed with gas. So, bus bars are the conductors which are taken from over large lengths from one place to another, and they are not necessarily always going in the same direction. Very often, these bus bars are typically coaxial cylindrical arrangements. So our discussion with respect to coaxial cylindrical arrangements will work here. So you have, as you can see in this picture, you have an inner cylinder and then you have an outer cylinder, and the space between the two is filled up with gas. It could be SF6, it could be other combinations of SF6 and other gases. Now, when this bus bar needs to change direction, you cannot just turn the cylindrical thing around, because in that case, the cylinders would have sharp edges, and therefore you need an interconnection. So, if you need to turn, you have a bus bar which is going in this direction, and then you have another bus bar which is connected at 90 degree. At the joint of these two bus bars, you will have, because you are needing to change direction, you will have a knee or an elbow, where you have a interconnection of a coaxial sphere with a coaxial cylindrical configuration. So these are the coaxial cylinders, and here at the edges of the two coaxial cylinder connections, you will put a coaxial sphere, and this coaxial sphere is going to interconnect the two. Now you need to, similarly as we have designed the end connections, here too we have to design the end connection. We have to design the interconnection. What should be the radii? So here I have, we are not talking about the earth walls of the laboratory as the outer conductors, as we did before in the previous slide. Here we are actually talking about a real coaxial connection. So you have small r1 as the radius of the inner cylinder, small r2 as the radius of the outer cylinder, capital R1 as the radius of the inner sphere, the spherical configuration that you will use as a knee, and capital R2 as the outer spherical radius. Now, we would like to optimize this interconnection. An interconnection of a coaxial sphere with coaxial cylinder configurations is optimized so that the edges of the earth conductors arising at the intersections are adequately rounded. That will also need to be done. Now, we know that the maximum electric field, the voltage is the same. So maximum electrical field in the cylindrical part is given by capital V divided by R1 ln R2 by R1. So if you have a particular value of Emax, then you can write V in terms of Emax as V is equal to Emax R2, R1 by R2 ln R2 by R1. So what we have done is we have expressed V as a function of everything else. We know what Emax should be. Emax should be typically the breakdown voltage, breakdown strength of the gas that you have here. And here we are going to use a very controlled gas, which will be very pure, which will be maintained at a given temperature and pressure. So we will have a better estimate of its breakdown. It will be closer to the predicted breakdown strength than in case of air, where air we don't have much control. Anyway, whatever is the breakdown strength of the material, we will consider that to be the Emax. Now, I want to optimize this cylindrical portion of my geometry. Now, R2 is fixed. Because R2 is decided by the space that is available to me. I am going to put my GIS in a particular location, and I know how much space is available to me where I can put it. So let us consider, R2, let us assume R2 to be fixed, and that is a kind of rational assumption. If I consider R2 to be fixed, then what I need to do is I need to search for an optimum ratio of R2 by R1 or R1 by R2 such that I can have the highest voltage I can apply to the conductor, and I would have sufficient insulation. Let me repeat what I'm trying to say. I have a GIS, and I know the outer diameter. That is decided by some factors, maybe because of the space available to me or the trench that has been dug. I have already decided what is my R2, that is the radius of the outer conductor, outer enclosure. Now, I also know what could be the maximum value of the electric field on the inner surface of the inner conductor. That Emax should be equal to EB, which is the breakdown strength of SF6 if SF6 is the insulating medium. Now what I would like to do is I would like to design the conductor radius, inner conductor radius, in such a way that I can apply the highest voltage without breakdown occurring. So the charging voltage, I want to increase it such that, so I want to decide R1 such that V can be maximized. So I'm going to look for an optimum value for the ratio R2 by R1. And I shall also consider R2 to be constant. So Emax is equal to EB. Let us treat R2 as constant. So what do I need to do? I need to find dV/dr is equal to 0 with respect to R1, which gives me ln R2 by R1 is equal to 1, which means R2 by R1 ratio, the optimum value of R2 by R1 is equal to E, which is about 2.72. So that means for this ratio, I will be able to have an optimum voltage level for my conductor, and that optimum voltage level at which I can charge my inner conductor is given by EB into R1, EB being the breakdown strength of the material. Now, if you consider R2 by R1 equal to E, the field efficiency factor, which we can calculate for the cylindrical geometry, the field efficiency factor can be calculated as 1 by R2 by R1 minus 1 ln R2 by R1. And this comes out to be 58%, which is quite high. I mean, it's an acceptable value. Now, even if you cannot design your system such that you have exactly R2 by R1 equal to 2.72, but if you can design with ratios very close to this optimum value, you will be able to obtain field efficiency factors which are pretty close to 58%, which is an acceptable value. So this kind of gives you a thumb rule of how to design the cylindrical part of your gas insulated line such that you are able to transmit considerably high voltages without stressing the insulation to any dangerous limits. So once we have optimized the cylindrical part, we now need to optimize the elbow joint as well. Now, if we proceed in the same manner, in the sense that we do dV/dr with respect to R1, keeping R2 constant. So again, here we are talking about capital R2. So dV/dr with respect to capital R1, keeping R2 constant, will give me R2 by R1 is equal to 2. In which case, the voltage, the optimum voltage would be EB R1 by 2. And the field efficiency factor in this case is R1 by R2. So, for the concentric sphere arrangement, the optimum values for the breakdown can be independently derived. I have independently derived by using the same methodology. I have independently obtained the field efficiency factors. And this field efficiency factor for the spherical arrangement is only slightly smaller for R2 by R1 than what you have found for the coaxial cylinder with optimum conditions. So these are pretty close together. Now let us optimize the arrangement, the total arrangement. So now, so far we have independently optimized the cylindrical part and the spherical part, and we see that independently optimizing them both get us to acceptable values. At the same time, we know the spherical is going to have a slightly higher breakdown strength. So what we will do is we will now optimize the total configuration. So if the bus bar is optimally designed, we will already have R2 equal to R1E. R1 can also be obtained from Emax is equal to V by R1 ln R2 by R1. For the given values of the breakdown voltage V is equal to VB and the breakdown field strength of Emax is equal to EB, we can now equate the values of VB by EB for the two systems. So once we have optimized the cylindrical portion, what we will now attempt to do is we will try to equate the values of the maximum electric field at the cylindrical surface, inner cylindrical surface and the inner spherical arrangement, just as before. We may select an optimum ratio R2 by R1 for the spheres. Okay, first when we equate the values, we get capital R1 into 1 minus R1 by R2 equal to small r1 ln R2 by R1, and this is equal to R1. So we must select the optimum ratio for R2 by R1 for spheres, and this gives me R1 to be equal to twice R1, twice small r1. And twice small r1 is, if you remember, relating it to R1e, so capital R2 will be equal to small r2 into 4 by e. So therefore, we now have the inner radius of the spherical arrangement as twice the radius of the cylindrical arrangement and the outer radius of the spherical arrangement as R2, the outer radius of the cylindrical arrangement into 4 by e. These conditions are quite favorable in practice. These are kind of practical values, achievable values, and therefore we can proceed with this. If you look at what gap distances you obtained, for the spherical arrangement you will obtain a gap distance of 2r1, and for the cylindrical part you will achieve a gap distance of r2 minus r1, which is equal to 1.72 r1. These conditions are quite favorable in practice, as the outer sphere diameter is not much bigger than that of the cylindrical system. The gap distance in this case is more, but you do not have a situation where you have a small cylinder capped by a huge spherical arrangement. So this optimization is quite acceptable.